Alright, so if we go over to MathCAD, we have our program that we made. We have this f of x, and what we're going to do is we want to see now how do we program the bisection routine. Okay, I'm just going to move this over here so that we can see most of this. Okay, so here we found the roots by doing the graphical method and using the trace function. And then what we really need to do now is create an algorithm that's called bisection. Okay, and so here we'll call this bisect. And this is a function that's going to take our upper guess, our xu, our lower guess, xl, and our stopping criterion, epsilon. Then we do the colon equal, and then come over here and we'll do add line, and we'll say we'll do a new function here, g of x, just to keep things clean, and we'll call it we'll assign f of x to it. So we basically are bringing this f of x in here to our program. And then the first thing we're going to do is calculate our root. Okay, and our xr is going to be and we can hit the / button. That's just xu plus xl over 2. Okay, and what that basically, what that is it's just the same thing here as getting xu and xl the first time and calculating this first xr here. Okay, so then we'll hit spacebar, highlight the whole thing, and then add another line, and we'll create some index variable. And the reason we do this is we want to count up to some number, and our stopping criterion is going to be when the epsilon value is low enough so that the relative error is low enough. And you can see our stopping criterion here is when the old root, the new root minus the old root over the new root times 100 is less than some specified threshold. Okay, so that's what I'm going to be using here. But say we don't get to our threshold, we don't want to get stuck in this loop forever and what's called an infinite loop, so we just want to create some I. We'll start off at 0, then we'll add a line, and we'll create an I max, and we'll set I max to 100. So no matter what, we're not going to go through this loop more than 100 times. Alright, now this gets into where we need to think in terms of programming and syntax. And what we need is a while loop. And a while loop just basically says that while something is true, execute all the code below. And what we want to do is we want to say while I is less than I max, go through here and do your bisection routine. Okay. So for the bisection, first we want to check the sign. So I'll just create some value called sign check, and I'll assign it to g of xl times g of xr. So that's over here in our program. This is f of xl times f of xr is the same thing. Okay, we're testing to see if it's less than 0. Alright, so this is our sign check. So we multiply the function evaluated at these two places, and then we say okay, this is still in the while loop. We add another line and we say that xu is going to become xr if sign check is less than 0. Okay, then we'll come down and we'll add another line and we'll say, well, xl is xr otherwise. Okay, so basically it says, hey, here's your sign check, evaluate g of x at xl and xr. It's the same thing as evaluating f of x at those two values. And then if it's less than 0, we make xu xr. Otherwise, we make xl xr. Okay, and that's the same thing that you see here. If it's negative, make xu xr. Otherwise, it's positive. And of course, for here we're not testing for the condition that it's 0, which we should have in the algorithm, but I'm just trying to get you up to speed here. Otherwise, xl is equal to xr. Okay, so that's the same thing that you see here. xl is equal to xr. Otherwise, okay. Now we need to come down here and add another line, and we'll say now that we have our new xl and xr, we need to calculate our new root. But before we do that, we want to keep track of our old root, so we'll call this xr old, and we'll assign it the value of the current xr. Okay, and then we'll come down here and we'll calculate our new xr, and we'll say that the new xr is equal to xu plus xl over 2. Okay, and then we'll say our relative percent error of estimation is equal to this bracket, and this is the line that's just above. I'm sorry, if you hold shift and it's the straight line above the enter key on my keyboard, probably most keyboards. And here we say that this relative percent error of approximation is xr. Okay, that's our new value, minus xr old, which is our old value, over our new value. Okay, times 100. Okay, and that gives us relative percent error. And the only thing we have to do now is break if EA is less than ES. Okay, so that's our algorithm. So we can add another line. Oop. Come over here. Okay, we'll add another line and we'll return XR. Variable is undefined. Maybe I think you have to pick this break. You can't type break. Okay. Alright, so now there we have our algorithm, and all we have to do now is see if it works. We have our roots up here. We have our function. And now we just need to pick our XU, we'll say is 8, which is above 6, and we'll say our XL is 5, and we'll say our epsilon is say, like, we'll call it 0.1% error. Okay, and then down here we can call this bisect, open bracket, XU, XL, ES, and then hit equals for evaluate, and we see this gives us 6.143. Okay, now if we made this error, this allowable error, larger just by changing this, we'll see that we get a larger error on the root. Let's say we allow a 5% error, and then we see this is a lot bigger than the actual value of the root here, which is 6.14. What we can also do is pick an upper limit of 0 and a lower limit of -5, and then we see we get close to this root. Let's bring this ES down here. We'll say ES is now, instead of 5, it's 0.5, and there we see we'll get much closer to the real root, 1.138. and we can even make this ES equal to say 0.05%, and it gives us the root. Okay, so hopefully this will help you out in your homework. Hopefully you see the syntax. If you have any questions, email me. Don't be overwhelmed. Just get in there and try to start making this work. Try to understand the algorithms. And obviously I've done this one for you. What you need to do is check for 0 and find a way to return a value for each iteration through the loop. So that you can get the relative percent error and the true error. The true error is the difference between the true root and the estimated root. So happy coding.